Okay, has it started? Yes, okay, so our second speaker for today is Suzie Brown, here from Warwick. And Suzie is going to speak about asymptotic genealogies for non-neutral populations. So Suzie, whenever you want.
Yeah, so thanks Diego for inviting me, if we can call it inviting. So this is about this is work I've been doing in my PhD, which is motivated by sequential Monte Carlo, but today I'm going more from the population genetics point of view, just to keep things fresh for those of you who've already heard this before. Okay, so what I'm going to do is introduce a class of models which is quite broad, and I will present some previous results, convergence results for this class or subsets of it, and then I'll present the extension to these results that we've obtained. So to start with, so we've got an interacting particle system, which I will explain its dynamics in a minute. But first of all, it has n particles, so we have a constant population size n, so this is the same in every generation. And each individual in the population, we assign a genotype, which is just a state, which we denote by x, which lives in some state space, curly x, which we assume is a subset of R to the D. And the index T is for the generation, and then the index I is indexing the individual in the Tth generation. And we initialize the particle system by just sampling IID, the initial genotype for each of these individuals from some distribution mu, which we assume is known. It's part of the model. So then the model dynamics. We start with, stop pressing the wrong button. Okay, sorry. So suppose we're at generation T and we have capital N equals 4 individuals in our population. And I've denoted their genotype in this illustration by just their position in this vertical line. So the first thing we do is we do some mutation, which basically means we're going to change the genotype somehow. So this gives us some new genotypes or new states for each of these individuals. And this is done using a Markov kernel, so that will simplify things a bit later. And we assume that these Markov kernels are known, they're part of the model as well. So in like the sequential Monte Carlo setting, we typically change the position of every particle at every generation, whereas like if we were looking at more a genetic model, it might be that most of the individuals keep the same genotype from one generation to the next. So mutations are usually considered to be rare, but you can also encode that, of course, in a Markov kernel. So then what we do is we can calculate the fitness of each individual. So this is just a measure of how good their genotype is at producing offspring, basically. So I illustrate the fitness by the bigger particles have a higher fitness here. And the fitness is calculated by some function g, which depends on the current genotype. And this is also part of the model, so we assume it's known. And there are lots of different ways of choosing it, depending on what application you're interested in, of course. So then finally, we have the selection step. So this is where we each individual is assigned some offspring, and we call the number of offspring of individual I nu I. And the number of offspring depends on the fitness. So an individual with higher fitness is likely to have more offspring. So this one, for instance, has 3 offspring. And these all inherit exactly the same genotype that the parent had. And then these, so because we're keeping a constant population size, we still have 4, we make sure we still have 4 individuals in this after the selection step. And these then make up generation T plus 1. So there are a lot of sort of degrees of freedom in the description of the model, but actually I'm not going to be looking at all at these kernels K or the function G. This isn't actually particularly of interest for what I'm going to talk about today. I'm actually going to sort of gloss over all that and just look at the relationship between the offspring and the parents. So I'm just interested in which parent had which offspring. And so, for instance, if we start with this example, we had 4 parents, and then one had 1 offspring, one had 3, and the other 2 had none. So we can draw this like this. So if these are the parents at time t, and these are the offspring at time t plus 1, then we can just represent the parent-offspring relationship with an arrow. And if we were to run the particle system for a few more generations, we might have something like this. So where do we get genealogies from, and what are they? So first of all, we can look at an individual in the final generation. So say this guy up here, and we can trace back the lineage by just following the arrows backwards. So this is like the parent, the grandparent, etc. And all of that together gives us the lineage of that individual. And if we trace back the lineage of all of the terminal individuals, we can get something like this. So I've just highlighted them here. And all of this information together, we call this the genealogy of these 4 individuals. And as you can see, we have lineages coalescing. So every time 2 of these lineages have the same parent, we get a coalescence of these kind of lines. So that's actually what we're mostly going to be interested in. So if I'm only interested in the genealogy of the terminal particles, then first of all, I can throw away all the information about these black particles because we don't see them in the sample at the end. They don't leave any descendants. And I can also sort of simplify this diagram a bit because actually all I need to know is which lineages coalesced and at what time. So we can then draw, instead, we can simplify this picture and draw something like this. So this contains all the information about the genealogy. And these vertical lines are corresponding to the generation, so like generation t, t plus 1, etc. And I won't go into the details, but we can encode this picture by a stochastic process on the space of partitions of the numbers 1 to n. And so I won't explain how we do that, but it's a fairly reasonable thing to do. So what I'm going to be interested in is the asymptotic genealogy. So this is asymptotic in the regime where the population size capital N is going to infinity. But we're still going to look at a finite sample size. So I'll put all that a bit more clearly in a minute. But first of all, we're just going to take a little detour and talk about Kingman's encoalescent. So this is like, this is a coalescent process, which is very famous in population genetics. It's arguably the simplest non-trivial coalescent process. So it's a continuous time Markov chain on the space of partitions of 1 to little n. So it's the same encoding, using the same encoding that I mentioned before. And the only transitions we have are single pair mergers, so like 2 lineages merging into 1 like this. And each of these pair mergers happens at rate 1 per pair, which means that when there are more lineages around, there are going to be more possible pairs, and so we get more mergers happening at a higher rate in total. So if you look at the bottom of this tree, there are a lot of lineages, and so you get a lot more mergers than like at the top, where it takes a long time for, say, the last 2 branches to merge. So yeah, this picture is just a realization with little n equals 50. So it's going to turn out to, just to give you a spoiler, that this is going to be a limiting process for certain classes of models of the type that I've introduced, but I will get to that shortly. So the scenario that we're in is where we have this population size capital N, although in a minute we're going to let that go to infinity. We are assuming that we have discrete generations, and that we're going to sample a finite number of individuals from the terminal generation. So these convergence results are only for finite samples. None of them are for the whole population. And then we're going to apply some timescale because if we just go back a minute, this was a continuous time process and we have discrete generations. So we need some timescale in order to get a continuous time process in the limit. And when I say appropriately, I mean that we want a continuous time limit, but we also want it to be something interesting. So not like a trivial case where nothing ever coalesces or where everything coalesces immediately, because those wouldn't be that exciting. So we're going to apply a timescale and then we take the population size to infinity and we'll see what happens. Okay, so the first result, which is from Kingman in 1982, who is the guy who came up with the coalescent, and then in the same year he came up with this series of 3 papers culminating in this theorem. So he assumes the case where the individuals are exchangeable. So that means that the distribution of the offspring counts doesn't depend on which individual you're looking at. It's sort of symmetric across all of the individuals. And he also assumes that these offspring counts are IID from one generation to the next. So they're independent between generations and the distribution is always the same in each generation, which means that we can drop the dependence of nu on t because they're all always the same, and we can just look at nu1 instead of looking at the general offspring counts. And then he has these 2 conditions. So the first one is saying that the variance of the offspring counts has to converge to a constant, and it's got to be finite, but it's also not allowed to be equal to 0, which I'll talk about in a minute. And the second condition is that all of the moments of the offspring counts are finite. So that's obviously a pretty hefty condition, and we're going to relax it a bit later. But first, a few comments about this. So under these conditions, we get weak convergence of these genealogies of a finite sample to the encoalescent when we take the whole population size to infinity. So what are these conditions actually doing? So exchangeability is how we encode neutrality. So this just means that we don't have any natural selection. That is, the genotype doesn't affect how many offspring an individual has. So this isn't a very realistic population model because we know that we get natural selection based on certain genotypes being fitter than others. But it's a good starting point. And as I said, we have this exchangeability and sort of time homogeneity. So the system is completely specified by the distribution of nu 1 to n. So here are 2 famous examples from population genetics which fit into this theorem. So firstly, the Wright-Fisher model, which is where the offspring counts are multinomial with equal weights. So this is the multinomial distribution is exchangeable. So we have exchangeability there, and it also satisfies the other conditions of Kingman's theorem. So that's an example where this holds. Another example is the Moran model, which is where the offspring counts are uniform over permutations of this vector that has a 2, 0, and then the rest are 1s, which means like everyone in the population has 1 offspring except for one guy who doesn't have any and one who has 2. And because it's uniform over permutations, that's essentially by definition exchangeable. So those are a couple of examples. Okay, and then what else do I want to say? So another thing to notice is that because we have a constant population size, that means that the sum of the offspring counts is going to be equal to n. And we're also assuming the individuals are exchangeable, which means that the expected number of offspring of each individual has to be 1. Yeah. Which means that if we took sigma squared equals 0, this is the case that was excluded, then we would have no variance, which would mean almost surely every individual has exactly 1 offspring, which would mean that we never get any lineages coalescing. So this would give us like a trivial limit where all the lineages stay separate forever, which is essentially why it's ruled out, because it's not very interesting and it's just a bit of a nightmare. Okay, so then this was a nice result from Kingman, which gave us sufficient conditions, but as I said before, these conditions that all of the moments are finite is a bit hefty, and it turns out that it's not really necessary. So a bit later, we have this theorem from Moehle and Sagitov. So again, we've got the same conditions about exchangeability and IID generations. But so now we introduce these 2 quantities. So Cn, this is going to be, this is like the second factorial moment. So, oh yeah, I should explain. So this like n brackets 2 means it's a falling factorial. So this is n times n minus 1. So this is a factorial moment. And this is just basically the interpretation of this Cn is it's the rate of pair mergers. So where exactly 2 lineages merge into 1. And then this Dn is the same thing, but with the third moments. And this is the rate of triple mergers where you have 3 lineages merging into 1. So the main condition is this one, that Dn over Cn converges to 0. And that means essentially that triple mergers are dominated by pair mergers, which is how we can expect to get something like the encoalescent in the limit, because if you remember, the encoalescent only allows pair mergers. We can't have any bigger mergers happening, so they need to happen on a slower timescale than the pair mergers, which is what this condition is saying. The condition that Cn goes to 0 ensures that we have a continuous limit, a continuous time limit, and yeah, I won't go into the details about that because it's to do with how we set the timescale as well, which I'm sort of avoiding, but we just assume we have an appropriate timescale, hence rescaled genealogies. And Cn greater than 0, this condition, I think I wrote it on the next slide actually. This is playing the same role as the condition sigma squared greater than 0 that we had in Kingman's theorem. It's making sure that we do actually have some coalescence events, so we don't get this trivial limit where nothing ever coalesces. So a couple of other things to point out. If you do a bit of algebra on this, you can work out that Cn is actually equal to the variance of the offspring counts divided by n minus 1, which means that Cn to 0 is a weaker condition than the analogous one in Kingman's theorem, which said that the variance had to go to a constant. And the main difference is that we now only require control on third moments via this dn function, whereas Kingman was requiring control over all of the moments, which is obviously a lot stronger. Okay, so what we have now is basically a full theory for the neutral case, because we've got necessary and sufficient conditions, so we're done basically. But what we were interested in was looking at the non-neutral case, which is kind of more interest in population genetics, in that the neutral case is quite restrictive because you can't see anything like natural selection, so it's not that realistic. And it's also, it was motivated by sequential Monte Carlo, which induces genealogies that are definitely not neutral because, well, I won't go into details, but you end up with like quite strong dependence on the of the fitnesses on the states of the individuals in sequential Monte Carlo. So we wanted to try and get similar results for the non-neutral case, which is what we did here. So the first condition here is our analog of exchangeability, but it's much weaker than exchangeability. So what it's saying is that if once we know the offspring counts, we just assign the offspring at random such that each parent gets the number of offspring that it's meant to. So this is kind of like saying that we can permute the children, but the exchangeability conditions in the previous two theorems that I showed you were saying that the parents were exchangeable, which is much stronger, because even under this condition, we can still have the number of offspring determining, like, being highly dependent on the fitness, whereas if you assume the parents are all exchangeable, then that means that you can't have any sort of selection. And then, yeah, and the other thing about this condition is that, like, it's easy to enforce in the setting of sequential Monte Carlo, which was something that we liked about it. So this very vague condition that the time scale is almost surely finite, I'm not going to go into too much because I haven't talked about the time scale today, but this is playing the same role as that sigma squared greater than 0 in Kingman's theorem, or the Cn greater than 0 in Moehle and Sagitov's theorem. It's just to ensure that we actually get some coalescences. Otherwise, we would end up with this weird trivial limit where nothing happens. So the main condition is this one, and I'm going to claim that this is essentially the non-exchangeable analog of Moehle and Sagitov's condition. So if we just go back for a second. So we had these two quantities, dn, which was like the third moments, and cn with the second moments, and we wanted to make sure that dn over cn was converging to 0. So now we have, again, something that looks like third moments and second moments. And again, we want the third moments dominated by the second moments. The difference is that now we have t explicit here because we don't assume this thing that every generation is the same. And we also have to be explicit about the index of the individual because we aren't assuming they're exchangeable. So we have to calculate this for each individual and then sum over from I equals 1 to n. Whereas in this case, we just put a factor of n out the front and just use the offspring counts of individual 1 to do the same thing. And then the only other difference is we have now our expectation has this subscript t on it, which it's a filtered expectation. I'm hesitant to go into any details, but it's essentially the upshot of this is that we can actually calculate this thing, because if we had to take an expectation without any conditioning, this would essentially be impossible in our setting. Yeah, hopefully that convinces you that this condition is somewhat like the Moehle and Sagitov condition, but way more complicated, because now we don't assume all these nice things about exchangeability and homogeneity. And we get this result again, that the genealogies converge weakly to the encoalescent. Actually, in this paper, we only have the proof for in the sense of finite dimensional distributions, but we have also proved it converges weakly. It's just not published yet. The only sad thing is that these are still only sufficient conditions, so we haven't proved that they're also necessary, although we sort of feel that they're close to necessary at least, because they're so similar to Moehle and Sagitov's conditions, but we haven't tried to prove that yet. And using this theorem, we've managed to prove lots of applications in sequential Monte Carlo, but we haven't really looked at yet the applications in population genetics, so that's something maybe we can come around to later. Yeah, so I think I'll just summarize at this point, so with some open questions. So as I've said, it would be nice if we could show that these conditions were necessary and sufficient, or similar conditions maybe, because we feel like they probably are close to being necessary as well as sufficient, but we haven't proved it. Another thing that I didn't really emphasize is that in this case, we have because everything depends on t, the timescale is no longer constant. So in the neutral homogeneous case, you can just take a constant function for the timescale and apply it at every generation the same, and it all works. But we have instead a random timescale that's different across each generation, which is fine for the technical results, but it's a bit complicated for if you want to actually apply it to anything. And particularly for our sequential Monte Carlo applications, it would be really nice to actually know what the random timescale looks like, how it behaves. So Moehle and possibly others also did some work on rates of convergence for the neutral case, so that could be something that could be done in the non-neutral case as well. And as I said, we've done lots of applications in sequential Monte Carlo, but it would be nice to have a look more from the population genetics side as well. So there we go, and there are some references.
Okay, thank you, Suzie, very much. Again, let's get a round of applause on the camera before I stop the recording. Okay, so now I stopped the recording, and